Swayam Prabha. Digital India. Educated India.
Friends, welcome to the lecture 34 of the course Advanced Steel Design. In this lecture, we are going to learn more about the stability problems, numerical example. We will deal with more numerical examples in this lecture and learn a couple of more with application to MATLAB programs. Okay. Before that, let us revise quickly that my stiffness matrix of the member is given by the stiffness matrix is given by the basic equation, which we should remember, similar to that of a beam, which is a 4 by 4 matrix. Which is Ri by Li, this is Ci Ri by Li, and these 2 by Li will be this. So, 1 plus Ci of Ri by Li square and negative of this. The second column is swapping of this, and sum of these 2 by Li and the last one is negative of the previous one. The third column is sum of these 2 by Li is also sum of these 2 by Li, and the fourth one is, the next one is sum of these 2 by Li again. So, I should say 1 plus Ci Ri twice, but I introduce a new coefficient Ti, okay, and this is minus of that. The fourth one, of course, is negative of the third one. This is what we should remember, which is similar to what we have in the beam application problem. Okay. Having said this, let us go to the example 3, as you see on the screen here. So, this example is about an orthogonal frame. It has got 2 members. One member is having length 2L, the other one is L. Okay. We have marked the degrees of freedom, as you see here. So, the degrees of freedom are marked as theta 1 and theta 2 unrestrained, okay, and remaining all are restrained. We are neglecting axial deformation. Okay, so restrained degrees. So it has got unrestrained degrees 2, which are theta 1 and theta 2, and restrained degrees are, let us say, theta 3, del 4, del 5, del 6 and del 7, which is about 5. So the total kinematic degrees of freedom is 7. Okay, so each matrix will be 4 by 4, and we can try to find out this very easily. So now for the member KAB or K1, okay, for the member K1, I should say R1, okay, by 2L, 1 plus C1, C1 R1 by 2L, okay. So 1 plus C1 of R1 by 2L square, sorry, by Li square, so that is 2L the whole square, okay. So the negative of this 1 plus C1 R1 by 2L the whole square. The second column will be C1 R1 by L, R1 by L, 1 plus C1 R1 by 2L the whole square, minus of 1 plus C1 R1 by 2L the whole square with a negative sign. The third column will be 1 plus C1 R1 by 2L or 2L the whole square. So 1 plus C1 R1 by 2L the whole square. The third one is 2 R1 T1, 1 plus C1 by LQ, so I should say 2L the whole cube and negative of this. The fourth column, of course, negative of the third column. So we have this. Let us mark the labels. We will take the jth end here and kth end here for this member. So we should say this is 1, 3, 7 and 5. 1, 3, 7 and 5. So rotation at jth end, rotation at kth end, translation along positive y. If I say this is my xm, anti-clockwise 90 is my ym, so this becomes my label 7 and this is my label 5. Okay, so K1 for the member AB is established. Of course, we have an EI multiplier outside, so we can do this. Okay. The next one is for the second member K2. So let us do it for the member K2, which is again EI times of, again a 4 by 4 matrix. So this is going to be R2 by L, because you see the length of the member 2 is only L, okay. The length of the member 2 is only L. So R2 by L, then C2 R2 by L, 1 plus C2 of R2 by L square Okay. So, let us mark the labels. Look at this figure. I am calling this as my j at the end and this as my k at the end. This becomes my xm and this becomes my ym for the member 2. So, I should say the labels are going to be 1, 2, 4 and 6. Okay. Let us mark them here. 1, 2, 4 and 6. Okay. Now, we can assemble these two matrices and try to get KUU. The KUU will be partitioned at 2 by 2. So, now I am try to get KUU because I have set determinant to 0 of this. So, let us KUU which is 2 by 2. Okay, let us do this to be 2 by 2. Okay. Let us try to get this. So, we should look into this figure. 1 1 is I have here. So, R1 by 2L. So, let me do it here. R1 by 2L. Then do we have 1 1 here? So, we have R2 by L as well. This is 1 1. Okay. Let us say 1 2 which is not in the first matrix, but 1 2 can be in the second matrix. So, 1 2 is C2 R2 by L. C2 R2 by L. Okay. Then let us say 2 1. 2 1 is here. 2 1 is the second matrix here. C2 R2 by L. So, C2 R2 by L and 2 2 is here which is R2 by L. Okay. Right. So, I want to set this determinant to 0 to get my characteristic equation. Okay. So, if I do that, I am writing it here. So, R1 plus 2R2 by 2L square minus C2R2 by L the whole square should be 0. Okay. So, this gives me the expression R1 plus 2R2 by 2L square into R2, I think into R2 because we have to product this R1 by R1 plus 2R2 by 2L square into R2 minus this is set to 0 which gives me the characteristic equation as R1 equals 2R2 times of C2 square minus 1. This is what we call as my characteristic equation. Okay. Right. Now, I want to also see what is my axial load coming on the section. So, if I say P critical of the first member, okay, look at this figure. For the first member, this is 2P. For the second member, this is P, is it not? So, first member, this is 2P, and for the second member, okay, let us I think use square brackets, okay, which will be P. So, by this logic, phi 1 should be 2P because phi is the ratio between the applied load and the Euler's critical load, which is pi square EI by L square. So, in this case it is 2L the whole square, okay, which will become 8P by pi square EI by L square. Am I right? Similarly, for phi 2, which will be P by pi square EI by L square. Okay? So, by this logic, comparing equation 1A and 1B, we can get the following relationship. Which will be phi 1 is A times of phi 2, equation 2. Okay, so we got a relationship, we got KUUR determinant as well. So, I am going now satisfy these two conditions. What are the conditions? So, I have to satisfy the characteristic equation, which is given by R1 is equal to 2R2 C2 square minus 1. The other condition is I must satisfy phi 1 is 8 phi 2. This is what I have to satisfy. So, let us run the MATLAB program to do this. Let us now run the MATLAB program and try to obtain the values. Okay, let us do that. So, friends, this is the program which you are going to run. You can see here the control equation is this R1 square, okay, R. Let us say R1 is equal to or R1 minus, okay, minus 2R2 times of C2 square minus 1 should be set to close to 0. If you simply say exactly 0, we may not be able to pick up the correct value of R1, R2 and C2 and C1 from the chart. So, closely, okay. So, let us closely pick up this and let us run this program. So, I get these charts. I think we already have these charts with us, we know, right. So, we know these charts of R, I and T. So, the answers are phi 1 is 2.96 and phi 2 is 0.37. So, I will go back here. So, I get phi 1 as phi 1 as 2.96 and phi 2 as 0.37. So, for these values, if you look at the chart, I get R1 as minus 4.6727, I get T1 as minus 5.7540 and I get C1 as minus 1.4628 and I get further R2 as 3.4878 from the chart, T2 as 0.6754 and C2 as 0.6127. So, now I can interpret P critical as phi 1 times of pi square EI by 8 L square okay, 8 L square. So, we will be able to get the critical load because I know phi 1. Okay, if I know E, I and length, I can get critical value, Euler's critical. Okay, it is very simple and straightforward. Let us go to example 4. We will go to example 4. So, let us draw this figure here. One end is fixed, other end is hinged, and this is also fixed. Okay, let us call this as A, B, C and D. This is of two length L, this is L and this is L, and this is member 1 and this is member 2 and this is member 3. This subjected to in a horizontal load of 2p here of the whole problem. Let us now mark the unrestrained degrees of freedom. So, I get rotation here theta 1, I am marking them in green, rotation here theta 2. These are my two unrestrained degrees of freedom. Let us mark the restrained degrees of freedom theta 3, del 4. If I say del 4 and I neglect axial deformation, I have del 4 here and I have del 4 here also. Okay, and this is del 5. Okay, this is del 6. And therefore, this is also del 6 because I am neglecting axial deformation. Okay, and this is del 7, and this is theta 8, and this is del 9. So, I have 9 degrees of freedom. The unrestrained degrees of freedom are 2, which is theta 1 and theta 2. The restrained degrees of freedom are theta 3, del 4, 5, 6, 7, theta 8 and del 9. So, which is 7. So, the total kinematic degrees of freedom are 9 and KUU will be of size 2 by 2 because there are two unrestrained degrees, and remember we are anyway neglecting the axial deformation. Okay. So, I can easily write KAB, I can write KBC, I can write KCD, okay, assemble them and KKUU. That is what I am going to do now. So, let us do that exercise very clearly, it is simple and we can do that. Okay. So, let us look at the labels. For the member AB, let us look at what are the labels. We will take the jth end here, okay. We will take the jth end here, I will mark it, jth end here and kth end here. Okay, this is my jth end and this is my kth end. So, let us mark a table quickly. Jth end is at B and kth end is at A, and the labels are rotation at J, rotation at K, deformation or displacement along positive Y at J and positive Y at K. Okay. Let us do it for the member BC. Okay. So, for the member BC, we will take the jth end here, so jth end here and kth end here. So, I should say the jth end is at C and kth end is at B, and the labels are rotation at the jth end, rotation at the kth end, displacement along positive Y at the jth end and at the kth end. Let us do for the member BD. Okay, for the member BD. So, for the member BD, which is horizontal, the length is of course 2L, we should remember that, and we will take the jth end here and the kth end here for this member. So, the jth end is at B, kth end is at D, therefore, the labels are 1 rotation, then 8, then 4 and 9. Okay, these are the labels. I do not think we have any difficulty in writing the stiffness matrices for all the 3 members. Let us quickly do that. So, I should say KAB, is Ei times of similarly KBC is Ei times of similarly KBD Ei times of. Remember, this is of 2 length L, okay. So, be careful about the length. We also know the labels. Let us write the labels. 1365, okay, that is for the member AB. For the member BC 2176, 2176, and for the member BD, we know the labels are 1849, isn't it? 1849. And we know the first value here is R1 by L. This is C1 R1 by L, 1 plus C1 of R1 by L and minus of. This is again C1 R1 by L, R1 by L, 1 plus C1 of R1 by L minus 1 plus C1 of R1 by L. 1 plus C1 R1 by L, 1 plus C1 R1 by L, 2 times of T1 R1, 1 plus C1 by L. Okay, these are all L square, friends. I am sorry. And this is L cube minus 2 T1 R1, 1 plus C1 by L cube. And the fourth column is of course negative of the third column. Okay, let us go to member BC. So, this is going to be R2 by L, C2 R2 by L, 1 plus C2 R2 by L square. So, C2 R2 by L, R2 by L, 1 plus C2 R2 by L square. Similarly, 1 plus C2 R2 by L square. Two times of T2 R2, 1 plus C2 by L cube and minus of this. The fourth one of course is negative of the third column. I am not entering it, okay. It is very simple to remember. Let us go to the member K3. So, it is going to be, I will do it here, R3 by 2L, 1 C3 R3 by 2L. So, 1 plus R3 of, sorry, one plus C3 R3 by 2L, the whole square and negative of this, C3 R3 by L, R3 by 2L. So, 1 plus C3 of R3 by 2L, the whole square, negative of this. So, this will be 1 plus C3 R3 by 2L, 1 plus C3 R3 by 2L. This is going to be 2 times of T3 R3, 1 plus C3 by 2L, the whole cube. This is square, is it not? And this is negative of this. The last column of course is negative of the third column. We can know this. So, now if I assemble K and partition it to 2, This is going to be KUU submatrix. So now I should write KUU here, which is EI common of, let me write this KBD somewhere here, okay. So 1, 2 and 1, 2, I am writing KUU, okay. So I should say R1 by L, that is 1 1, then I get R2 by L, then I also get R3 by 2L, okay, this one. Let us now do 1 2. So 1 2 I can pick up from this, which is C2 R2 by L. Then I should say 2 1, 2 1 I should pick up from here, which is C2 R2 by L. Then I should say 2 2, 2 2 I will pick up from here, which is R2 by, right. I should set this determinant to 0. So let us multiply this and minus of this. Let us do that. So I can write that, which will be, I will copy this matrix. Okay. Let me put it here. Let me rub this. So I should say R1 by L plus R2 by L plus R3 by 2L times of R2 by L minus C2 R2 by L, the whole square should be set to 0, am I right? Which will be equal to 2R1 plus 2R2 plus R3 by 2L square of R2 minus C2 square R2 square by L square is 0, which will become 2R1 plus 2R2 plus R3 times of R2 minus 2 C2 square R2 square should be 0, am I right? R2 times R, 2R1 plus 2R2 plus R3 is equal to 2R2 square of C2 square. So let us say R2 goes away, okay, R2 goes away. We can say 2R1 plus 2R2 plus R3 is equal to 2R2 C2 square. So that is my characteristic equation, the control equation to develop this. Furthermore friends, please see this figure. I should say the axial load on the member 1, the axial load on the member 1 is 0, the axial load for the member 2 is also 0, the axial load for member 3 is 2p compressive, am I right? So by this logic, can I say phi 1 and phi 2 will be 0, because P1 and P2 are 0, am I right? So let us say phi 3 is 2p times of pi square ei by 2l the whole square, which will be 8p by pi square ei by l square. Let us keep this information with us to compute my critical load. Okay. So, I have got two control equations now. One is the characteristic equation, other is this relationship. I must now select phi in such a manner from the chart to satisfy equation 1 and equation 2. This is equation 2, sorry, and equation 1 is this. Let us run the MATLAB program and get the answer. So, now I am running the MATLAB program. So, this is the program, friends. Okay. So, the control equation is this. Okay, this is what we have. So, we can try to run the program and we get phi as 3.51. Okay, that is phi 3. Okay, 3.5. So, we should say phi 3 was found to be 3.51 and the corresponding R1, R2, sorry, C1 and T1, R2, C2 and T2, R3, C3 and T3 can be found out from the chart. I am not writing it here, so we can do that. So, if you have this value as 3.51, okay, so I can write PCR is equal to phi 3 of pi square ei by 8 L square. So, this is known if I know the cross section, if I know the length and if I know the E value, I can find the Euler's critical. Okay, friends, let us do one more problem. Example 5. You can now see a single bay, single story frame on the screen. So, I can quickly write some inferences. The unrestrained degrees of this problem are 2, which are theta 1 and theta 2, and the restrained degrees of this problem are 3, 4, 5, 6, 7, 8 and 9. So, 7. The total kinematic degrees of freedom is 9. So, KUU will be of size 2 by 2 because the understand degree is only 2, and each K, that is KAB, let us say this is my A, this is B, C and D. So, KAB will be of size 4 by 4, KBC will be of size 4 by 4 and KCD will be of size 4 by 4. Let us write down quickly the labels for these. Okay, let us quickly write down the labels. So, let us make a table for the member AB. Where is my J at the end? Where is my K at the end? Okay, and what are the labels? We will keep for the member AB, we will keep this as B and this as A. So, the labels are going to be quickly rotation at J, rotation at K, displacement at J and displacement at K. For the member BC, we will keep the J at the end at B and this at C. So, the labels are going to be 1, 2 4 and 7, and for the member CD, we will keep the j at the end at C and this at D. Therefore, the labels are going to be 2, 6, 9 and 8. So, friends, I think we can write easily the stiffness matrices of all the members. Let us do that quickly. So, KAB will be E times of R1 by L 1 plus C1, C1 R1 by L, then 1 plus C1 of R1 by L minus of this. Similarly, L square. So, C1 R1 by L, R1 by L, 1 plus C1 of R1 by L square and minus of this. So, 1 plus C1 R1 by L square, 1 plus C1 R1 by L square, 2 times of T1 R1, 1 plus C1 by L cube minus of this. The fourth column is simply negative of the third column, and the labels are 1, 3, 9, 5. Is it not? 1, 3, 9, 5. We can also write quickly for the member KBC, which is going to be E times of R2 by L, C2 R2 by L, 1 plus C2 of R2 by L minus of this L square, C2 R2 by L, R2 by L, 1 plus C2 of R2 by L square, negative of this. So, 1 plus C2 R2 by L square, 1 plus C2 R2 by L square, 2 times of T2 R2, 1 plus C2 by L cube minus of this, and the fourth column will be negative of the third column. The labels are going to be 1, 2, 4 and 7. You can see here 1, 2, 4 and 7. So, let us do it for K CD, which is E times of, we should remember the length is 2L in this case, is it not? It's 2, no, it's also 2L in this case, so we have to be careful. Okay, even this also 2L, even this also 2L. So, we should, I think, write 2L, 2L, 2L the whole square, okay. Right. KBC is just only L, that is okay, and KCD we can enter this, which will be, I will do KCD in the next slide. So, KCD EI times of which will be R3 by 2L, C3 R3 by 2L, 1 plus C3 of R3 by 2L the whole square, negative, and this value will be 2 times of T3 R3 1 plus C3 by 2L the whole cube, negative. So, negative, negative and plus of this column. So, the labels are going to be 2, 6, 9, 8. You can see here 2, 6, 9, 8. So, we have all the 3 matrices, I can assemble them and get KUU, which will be E times of, okay, substituting, we will get this as KUU. So let us say, for example, I should 1, 3, 9 and 5. So I am looking for 1 1. So I should get this and this. So R1 by 12 plus R2 by L. So R1 by 2L plus R2 by L. 1, 2 and 1 and 2. Let us do for 1, 2. So 1, 2 is here, C2 R2 by L, C2 R2 by L. So let us say 2, 1, 2, 1 is here, C2 R2 by L. So C2 R2 by L. Let us go for 2, 2. 2, 2 are 2 places. Let us say R2 by L, okay, R2 by L plus, then we also have R3 with 2L, right. Okay. So now let us set this determinant to 0. So I can write that is going to be R1 plus 2R2 by 2L, see here, R1 plus 2R2 by 2L into 2R2 plus R3 by 2L should be equal to, I can say should be equal to C2 R2 by L the whole square, right, C2 R2 by L the whole square. So this gives me rise to the characteristic equation, which will be R1 times of 2R2 plus R3 plus R2 times of 4R2 plus 2R3 should be equal to 4R2 square C2 square. That is my characteristic equation, which I will use the MATLAB now and do it. But further, let us also write phi 1. See the figure. Phi 1 will be P, phi 2 will be P, whereas phi 3 will be 2P. Okay? So let us do that. So phi 1 will be P by pi square EI by L square, which is 2L the whole square, which will now become 4P by pi square EI by L square. Okay. Let us say phi 2 is P by pi square EI by L square, whereas phi 3 will be 2P by pi square EI by 2L the whole square, which will become 8P by pi square EI by L square. Okay. So now I can write a relationship where phi 1 is 4 phi 2 and phi 3 is 8 phi 2. Okay. Let us run the MATLAB program. For the fifth problem. Okay. So this is the fifth problem. We have the program here. We have the control equation, which is here. Okay, set to close to 0 0, okay, not 0 0 0. Let us run this program. I get, these are the charts of R, T and P. I get phi 1, phi 2, phi 3 as you see on the screen. Okay. So let us say phi 2 is 0.38 and phi 1 and phi 3 can be obtained. Okay. I will minimize this. I can now say phi 2 is 0.38. I can find phi 1 and phi 3, does not matter. So for this I get R2 C2 and T2. Okay. I got R2 as 3.4738, sorry 32, C2 as 0.6660 and this is this is T2 and this is C2 which is 0.6165. So now I can say PCR is phi 2 times of pi square EI by L square. I have phi 2. Okay. If you know E, I and L, I can find PC. So friends, in this lecture, we also learned 3 additional numerical examples to find Euler's critical load. This book is a very good reference which you must use for stability functions, derivation, understanding more problems and computer programs in MATLAB. You can download them and this book is available in open access. So please see the book and try to use it for your library. Recommend it to your library and use it thoroughly. The MATLAB programs are available in this book. You can copy paste them and run them. These are the typical charts what you will see when you run the program. So friends, practice more examples in stability problems, and if you have any difficulty, you can always discuss it in the forum and we will try to help you out. Thank you very much and have a good day. Bye.